Hello and welcome to my presentation for Advanced Construction Technology, the analysis of two complex buildings, the Sagrada Familia and the How to Yin Yang. The contents of this presentation will include the following: the substructure, superstructure, materials and constraints for both buildings, followed by a comparison of both buildings and a brief summary. Firstly, the Sagrada Familia. The most iconic landmark of Barcelona has taken over a whole century to build and is still not complete. Gaudi started in 1883, influenced by Mother Nature for the design, having taken over from the previous neo-Gothic design from the architect. Originally, 360 pestas a year were donated for the project. It was estimated it would take 10 years to complete. But by 1914, over 3 million pestes had been donated, and it wasn't even halfway through construction. It now generates 25 million a year, and that covers the cost for the maintenance and the annual construction costs. This shows how quickly costs can inflate and increase due to design changes, social factors, and other external factors to the project. World War I inflicted considerable delays to the project. Gaudi even went knocking from house to house for donations to push the project forward, as all work had stopped and all donations had stopped. In the 21st century, this wouldn't happen. There are banks for loans, there's the opportunity for mergers with other clients, and there is grant funding available. It's now considered whether we even finish the cathedral together or whether we preserve Gaudi's image and keep it as it is. Gaudi is unlike any other architect. He had no preset plan when he initially started on site. He preferred to let the project evolve through construction and see where the site laid and how the materials fell in the structure. The project started in the early 1800s using traditional construction methods, long before the HSE existed. It can be shown in these early pictures that there was no personal protective equipment on site, no safety restrictions, and most men were hand digging using a shovel for the trenches. The majority of the structure was covered in wooden scaffolding till the mid-20th century, and no cranes were seen on site. Cranes weren't added to the project until 1965, when they became more popular in construction around the world. Back in 1892, it has been shown that several hoists were used whilst building the crypt for the Sagrada Familia. It had a wooden structure and a system of pulleys with ropes. This is very much like the machinery used today, but a basic, simple version. These tools pushed the modernism of construction and where we are today. The substructure was constructed in an unusual way. The foundations for a specific section were laid, and then the following external walls for that area were constructed, whereas with modern methods, usually the foundations are fully laid first, followed by the external walls. This is usually because the entire building will need the foundation laid structurally before any more works can be done, or it could be because all of the foundations have to be laid as it's stated in the contract that the funding and other money is released once you've reached that point. Now work has commenced back on site, it's a very different story. Technology has been widely used to speed up the project and retain the precision and accuracy of Gaudi's image. To name a few of the technologies used, there is precision with Industry 4.0, which I'll cover in more detail later on, laser scanning and IoT to make and remotely move pieces of machinery safely and efficiently across the site without a human touch. Projection has been used with the 3D printing and modelling to create the mini version of any required sections of the building before any major construction starts. This shows any potential conflicts or issues before any costly mistakes are made, reducing the risk of the project. VR headsets are also used to walk around the project and make the design decisions much quicker. This has all helped overall to reduce the construction programme, but also to preserve the building as it currently is, whilst continuing to build with the authenticity that Gaudi would have wanted himself. The purpose of the Sagrada Familia was to be built as a big book for observers to read, not just as a cathedral, symbolising the body of Christ. It was to encapsulate the realistic, symbolic presentation of Christ appearing as a human on earth. The building is enormous and when completed will be the tallest religious building in the world, consisting of 18 towers in total, 12 of which are allocated to represent the apostles. However, it wasn't an easy journey. There were issues with civil engineering due to the gigantic columns and flying buttresses. Gaudi overcome this by a fundamental discovery. The interlinking parabolic arches and slanting columns can bear the weight of much more than an ordinary column. He himself would be overseeing the construction as well as being the architect, which is incredibly unusual in these days as they have two different skill sets and require two different teams to work on. He would hang weights from the ceiling in order to see how the structure would fall and create a design that would incorporate this as to complete the rest of the building. Another structural issue was the roof loading and lack of light. In order to overcome this, Gaudi designed skylights between the columns based on hyperbolics. Another example of where Gaudi had to think outside of the box to become the contractor and structural engineer. In 2014, Arup were asked to assist with the structural design. This was an extremely complex job as the traditional masonry and earthquake-resistant concrete stone cladding made the towers too heavy for the existing foundations. Instead, they used a scheme with the stone itself as a structure, producing the original finish and reducing the weight by a factor of 2. This approach not only reduced the construction program, but also reduced the build cost. This is where they brought in technology and used the Precision Industry 4.0 tool to create pre-stressed stone masonry panels as the primary structural element. The digital model is then used to automatically cut the individual blocks of stone that are accurately fabricated into a panel using laser-cut plywood templates. Pre-stressed with machined stainless steel bars. The pre-stressing gives greater strength to the panels, allowing them to be accurately fabricated off-site. This solution allows the panels to resist the stress imposed by the wind and earthquakes, but also to speed up the program. Again, technology assisted with the design, with all components being modelled by a 3D printer to a construction level of detail. Even the nuts and bolts were designed in this way. Panels were then craned into position, slotting exactly into place, needing no adjustment. It was critical the structure would echo the pure masonry construction from the 1800s, whilst allowing the modern off-site manufacturing to guarantee the high quality required. This method saves construction time, ensures the safe building processes, and maintains the original quality. Due to the nature of the building, panelization, modular construction, and 3D printing on site are not appropriate to continue the rest of Gaudi's work. The building is constructed from traditional masonry, concrete covered in stone cladding and stained glass windows. The stone was traditionally handcrafted for texture and authenticity. The stone includes variations of sandstone and granite, as well as reinforced concrete for the naves. This is a traditional Catalonian construction method, consisting of 2 to 3 layers of overlapping tiles woven together with a fast-setting mortar. This construction method is not used in modern buildings today, due to time, cost, and the awkwardness of materials on site. Currently, all of the materials used on site today for this project are the same stone and concrete used in the original construction to keep within the design brief. However, modern methods of constructions are used to cut the stone instead of handcrafting, but yet still get the same desired effect. In 1984, the Sagrada Familia became a UNESCO World Heritage Site due to the unique architecture and Gaudi's ability to create something so innovative and artistic. This is a high award and creates many restrictions on not only the site, but building methods and the materials used. This determines that the following legislation must be considered for any further works. Firstly, Law 16 of 1985 concerning the Spanish historical heritage. Secondly, Law 9 of 1993 concerning the Catalan cultural heritage. And finally, the decree in 2005 concerning the territorial commissions for the cultural heritage. These 3 laws place obligations on the design team in order to conserve the original building and maintain the material, form, and workmanship. They must maintain the significance, history, and the legacy of the building, however, balancing the cost with the social, cultural, and environmental factors at the same time. This requires a specialist contractor to undertake these works. The current work must consider the overall project which was planned originally, with the evidence and guidelines which have been drawn up and scientifically verified throughout. Overall, Gaudi is not considered a green architect, nor the Sagrada Familia a green building. However, he looked to nature to address the design issues he found throughout, which is the main reason for sustainability today, to look to nature. Additionally, Gaudi used natural lighting throughout the entire building, taking extra measures to protect the interior spaces and their lighting. This matches quality 8 of their LEED Indoor Environment Assessment. It must be noted that if technology had not been used, it would have been incredibly time-consuming, costly, and extraordinarily complicated to start the rebuild, potentially impossible. Therefore, it is crucial the methodology involves with the modern construction methods. By no means has this project been smooth. Back in World War I, the project ran out of funding, as previously mentioned, which stopped all works whilst Gaudi fundraised. Followed by the Civil War, where a group entered, vandalised, burnt areas and smashed models in the cathedral, which meant the design team had to stop building and spend time recreating all the designs and drawings. These days, there are high levels of security to prevent such attacks on site. Today's construction faces many challenges, also, as it was discovered the council had not originally granted a building permission. After 2 years of discussion, on the 7th of June 2019, the Sagrada Familia had its building permit approved, 137 years after the original application for a licence from the City Council. If this was to happen in 2020, you would be arrested for not having a building permission and had started building. Once construction had recommenced, adapting to the modern construction methods, the towers started to grow. However, measures had to be put in place, including agreeing with the Barcelona City Council to improve relations with those who live in the area by changing the work schedule. Therefore, the site no longer uses whistles to mark the beginning and end of the workday, as well as taking into consideration maintaining the opening hours for visitors in order to generate the vital income the construction needs to keep going. The next building to analyse is the How to Yin Yao. This is not your average residential tower block. It was designed by a Paris-based architect, Vincent Calibau, who wants his buildings to be more than an average tower block. His vision is to create an energy-saving, carbon-absorbing civilization to fight off global warming. The concept of eco-construction for residents to reduce the city's carbon footprint. The building was built in the image of nature and life itself, and the purpose was to change the way modern construction progressed and sustainable construction was viewed. It's also known as the carbon-absorbing tower with a vertical forest, and will be referred to as that for the rest of this presentation. The first mobile building was built in Dubai in 2011. The tower followed suit in 2013, but with a more complex design. The structural design, designed by the structural engineers King Lee Chang and Associates, won the CTUBH Initiative Design Award due to the complex nature, as the building needed to be designed to withstand high earthquakes, high winds, and intense storms, ensuring the sturdiness and durability throughout. The substructure consisted of 68 pile foundations, each with a 2.5 diameter, hammered 50 metres deep into the weight-bearing level, spreading the entire building structure to the most solid bedrock. This, along with the building's shock-resistant system, increased the construction costs by 3 times. Subsequently, through many reviews and national-level structural accreditation, the tower becomes the only residential tower in the world that adopts such a high level of structural design. Within the foundation design, there is a circular retaining wall, constructing a complete pressure-resisting circle balancing the outer forces. There is a shock insulation gap between the walls, which will dissipate the earthquake's movement, offset and absorbing the momentum, whilst creating natural lighting and ventilation for the basement. Furthermore, the natural light conserves energy in the basement and reduces the building's overall carbon footprint. The 21-storey residential tower has a special rotating shape, emulating a DNA double helix. The radical design is supported by a radical structural system, allowing the living areas to be column-free in each unit. The SS structure is built from high-strength steel rebar, which is the same used in other buildings in Taiwan. The meg columns use another imported high-strength steel. The unique structure, as shown here, is composed of 5 elements: central steel core tube, the multi-storey roof outrigger truss system, 2 sets of rotating mega columns, truss systems at every other level, and ESP shock insulation systems. These elements at foundation level are integrated with 48 friction pendulum isolators to ensure the maximum stability for the earthquake. All structure components are designed to remain elastic far beyond the building code requirement. This is modern technology at its best, pushing the boundaries of construction. Never before has a residential building in the middle of a capital city, known for earthquakes and major storms, has been constructed. Back in the 1800s, this wouldn't have even been possible. The 20 inhabited stories in the double helix stretch themselves and twist at 90-degree angles. This complies with 4 of the project's objectives. The first objective is to be perfectly integrated in the north-south pyramidal profile of the building's volume, allowing maximum sunlight in each apartment. The second is to create maximum space possible for the suspended open-air gardens, which are planted balcony surfaces for each unit. The third is to give residential exceptional panoramic views of the skyline of the city. And the fourth is to create the intimacy, privacy, and confidentiality of each apartment by avoiding the indiscreet vision axes. The facade is mainly made of glass, which is great for natural light within the units, but equally for creating a lighter-looking building, rather being made with the heavy, dense stone. The green tower combines both passive and active systems as it integrates green vertical platforms and living facades with human and natural climates. Not only is it a green building, but it contributes to the progression of sustainable energies, solar and wind generated power, with biological and biotechnologies. These using bioclimatic passive systems to create a carbon-absorbing tower. This is one of the first globally, demonstrating how sustainability, technology, advanced construction, and renewable energy sources can be combined to change the current construction industry. It must also be considered how sustainable construction can aid social and economic factors. Bike stores, intelligent lights, natural ventilation, and recycling energy are just a few of the factors the industry considers in everyday practice. These are all internal components of the building and that the residents must address themselves. The tower has all of the above in, however, the human factor must be considered and they will need reminding to take advantage and use them in order to maintain the building's low carbon footprint. The structure of the building is self-sufficient, however, the renewable energy plant on the roof will need regular maintenance checks. The balconies are covered in 23,000 trees and shrubs. Together, it is estimated the building will absorb around 130 tonnes of carbon dioxide a year. That is additional to the reducing the carbon dioxide the building produces. That is to absorb the output of the rest of the city. Moreover, they'll create a noise barrier to the city and the residential units. Another feature of the tower that can't be missed is the flowing waterfall through the ground floor and the basement. Its purpose is to create nature's beauty and create a sense of serenity for the residents that are living there. This is the first of its kind, revealing the collaboration of human actions and nature and the positive impact it has. As Vincent considers himself to be an ecological architect, he has also incorporated solar and wind-powered systems on the roof, supplying electricity for the whole building. This reduces the carbon intake by 35 tonnes. The main justification for having both wind and solar power sources is due to the location of the building in the city centre. Some days the smog is so thick, the solar panels are not effective, therefore the wind supply would take over. This is in order to account for all situations and keep the building sustainable throughout the entire year. Furthermore, the core cylinder of the structure is used as natural ventilation to reduce the temperature inside and decrease the requirement for air conditioning. Lastly, the building incorporates a rainwater recycling system installed to feed the ground floor sprinklers and ensure all construction and furnishing materials for the building are selected through recycled or recyclable labels. This is in order to keep the carbon footprint of the building as low as possible. Initially, Taiwan had limited planning processes compared to other parts of the world. However, for certain schemes in the city, they adopt the UK planning permissions and building regulations. How to Yin Yang is an example of one of those schemes. Nevertheless, the architect was Paris-based and knew how to use them, which minimised the risk of the project. This was not a simple project to undertake. The design team developed all structural, seismic, interior design and landscape design in line with the client's following 4 objectives. First, sustainability. The tower encapsulates the image of sustainable residential eco-construction, which restricts the footprints of the residents by balancing human and nature, coexisting through climate, landscape, and architecture. The bioclimatic was increased through thermal sunlight and wind energy sources. The second objective was for a green tower. The client required a high open space floor area, but equally high green coverage. Compromises were made in order to achieve both. For example, open space was sacrificed for a green wall surrounding the residencies. Another constraint the design team faced was a desire for flexibility, where the client requested each unit was to be completely free of columns, pipes, and walls, presenting a maximum of flexibility for the interior layouts. The structural engineers took this into consideration, and every other floor had beams along the longitude facade and the other floors without any beams, ensuring flexibility. However, this must be noted, this is not a usual design concept. Lastly, the most critical constraint was the anti-seismic tower. The same level as US roads and bridges of ESP isolation cushions have been used in this construction to ensure the complete safe environment for the residencies. This is typically an over-designed area for standard buildings. However, given the circumstances of where this particular building is situated, it is a necessity. All of these challenges were undertaken by specialist contractor Yuan, whose main aim is to use the breadth of expertise to design and construct projects which are environmentally friendly and will improve the quality of life and satisfy the needs of society, as well as using a consistently high standard tailored to each client. The main constraints and risks for the building was not the usual. The cost of the project, although considered, was not a high priority for the client, as seen by the tripling budget. However, the programme was, due to the urgency of finding residents to pay rent and earn an income from the building. The main purpose of the building was to make a statement in the city and to the rest of the world. What can be achieved with ecological construction? Both of these buildings have a lot of similarities and differences. For example, neither project considered cost to be a priority risk factor, even though the project tripled in the case of the tower, and the Sagrada Familia, it's so big now, I can't even count it. The differences are the Sagrada Familia, due to the time it was originally built in, started to use traditional construction methods. Then, due to the heritage laws put in place, had to use the modern methods to be adapted to continue to use those same traditional construction methods. Whereas the tower had one modern method used throughout, which explains why it's a finished, complete building, whereas the Sagrada Familia has differences throughout. This is also shown in the design, where the tower had one architect and design team compared to the many architects taking over somebody else's work and making it their own with the Sagrada Familia. This is not unusual, as it's taken 137 years to construct so far, but it does mean that there are differences throughout the entire building, and it's not one artist's complete vision. However, saying that, both of the buildings have been made in the image of something. The Sagrada Familia has been made in the image of God, using nature for design elements, whereas the tower has been made in the image of nature, using the human DNA as a design feature. Both buildings are currently being built within the 21st century, even if the Sagrada Familia wasn't originally. They both use computer technology such as laser scanning for site surveys in order to predict the exact quantity and be able to do an accurate drawing for the building quantities needed. The tower uses technology to harness renewable energy sources to power the buildings, such as solar and wind. Due to the conservation and heritage laws surrounding the Sagrada Familia, it is impossible to add those into that building currently. However, it is assessed in other ways, such as using renewable sources to transport the stone from off-site to on-site, using local labour sources, etc., etc. The materials for both buildings for the external facade are consistent. They both use one material throughout. The Sagrada Familia uses stone and the tower uses steel. The tower is made of a lightweight, easily produced cheap steel, whereas the Sagrada Familia is made from a traditional dense stone cladding, which is expensive and time-consuming to make. Both have their pros and their cons, but they equally make an impact on the eye. They both have key features of the impressive facade, and they both push the boundaries of construction methods of their time. One is an eco-friendly residential tower, and one is a traditional cathedral built in Barcelona. However, the technology and knowledge was not available back then when they started the construction. To summarise, they are both two incredible, awe-inspiring complex buildings, both pushing the boundaries of construction in their relative time periods, one progressing eco-construction and pushing the boundaries for that, one progressing historical and structural developments of its time, and progressing the conservation and heritage developments of today. How would the Sagrada Familia have progressed if they'd have had today's knowledge and technology? Who knows? It could have been a completely different building. It may have been finished now. That's one that we will never know. Both of these buildings have a lot of similarities and a lot of differences, but they both show what construction can do and how differently they can affect the world. Thank you for watching my presentation. Here is a summary of the references used throughout.